Many equations in physics relate, for example, how a system is going to change in time in the future based on how it looks in space now. It's very common for the future evolution in time to depend on the derivatives in space. For example, how a cloud of smoke disperses over time depends how concentrated it is in space to start with. And such behavior, for example, is often explained by something called the diffusion equation. Another very common and important example, and the one we're going to use here as an illustration, is the behavior of waves. Since these involve derivatives in space and time, they are necessarily examples of what we call partial differential equations. Now, this terminology with partial in it does not mean that they are incomplete in any way. It just indicates that they contain partial derivatives. Many waves in classical physics are described quite well using a particular differential equation, often just called the wave equation, and we will introduce this now. There are, in fact, actually several quite different wave equations for different physical phenomena, and an important point is that the main one we are going to use in quantum mechanics is actually not of this form I'm about to give you. But this particular classical wave equation is still a very useful example.
So let's look at a wave equation then as a good example of a differential equation. And the one we're going to look at here is sometimes called a one-dimensional scalar wave equation, and it comes up a lot in classical physics. So this is the equation we're going to look at. This equation has got the second derivative with respect to position here, and the second derivative with respect to time here. And this relates how strongly curved a function is in space, how strongly curved phi is here, to the second derivative in time, or the second temporal derivative. We could write this more completely, specifying that this derivative here is taken with constant time, and this one here is taken with constant position. But again, usually that's fairly obvious, so we will not bother to use that more complete notation. Now, for this equation, we can easily check the following. Any function of the form f of z minus ct, or indeed any function of the form g of z plus ct, are solutions here. So we can check this by the chain rule. At some time t0, we'll create an auxiliary variable here we call s, and that will be z minus ct0. So differentiating f of z minus ct0 by z, we use the chain rule formally, so that's df by ds at constant s. And notice this one is just an ordinary derivative because there's only one variable involved here in this expression of the function. And that's evaluated at the point s equal to z minus ct0, because that's where we're doing this differentiation. And then we're going to differentiate that variable s, this auxiliary variable, with respect to z at time t equals t0. So this is a chain rule used for partial derivatives. And in this case, ds by dz at time t0 is just 1. In fact, it doesn't matter what the time is in this particular case. And so, using the chain rule, partial df by dz minus ct0 here by dz is actually the same as df of s by ds, evaluated at this value of the variable s. We can go on to the second derivative. We're taking the derivative of df of s by ds, because that's what we figured out the first derivative here turned into. And again, using the chain rule, that becomes the second derivative of f of s with respect to s, again evaluated at this value of s. Again, times ds by dz, which of course is just 1 again. And so our second spatial derivative, the partial derivative, turns into this total derivative here, evaluated at s equals z minus ct0. Similarly, at some position z0, with rewriting our auxiliary variable now, giving it another form as z0 minus ct, we can do the same kind of operation on figuring out the time derivative, and it follows the same procedure here, but note that ds by dt is minus c, not just 1 that we had before, but minus c because we've got minus c here. So ds by dt evaluated at z equals z0 is minus c. And so we get a minus c in front of our first derivative here. And similarly for the second derivative, we proceed in a similar fashion, but we get yet another minus c coming in when we do this derivative here. So we've got c squared here, and we've lost our minus sign because we got a second minus c came in when we did this derivative. So putting this all together then, at some position z0 and at some time t0, our partial differential equation has been turned into an ordinary differential equation here. And we can see that this all equals 0. In other words, we have proved that a function of this form, f of z minus ct0, does indeed satisfy the wave equation, because this was the wave equation that has to equal 0, and indeed it does for this function f of z minus ct0. So we did not have to say anything about this function other than that it has particular derivatives that are well defined. And we can do the same thing for g of z plus ct. So let's look at what these solutions mean, and one of these turns out to be what we call a forward wave. The difference between this function at time t1 and the same function at time t2 is simply that we have shifted the function over. So if f of z minus ct1 looked like this, then f of z minus ct2 is just the same thing shifted over, here presuming that t2 is greater than t1. So moved over by an amount c t2 minus t1. So this is a function that in time, as time goes forward, this function is moving to the right. It's moving to positive values of z. So let's just look at that. The wave is moving to the right with velocity c. Similarly, if we look at the other possibility, the g of z plus ct1, then the difference between this function at t1 and this function at t2 is that this function is shifted to the left by an amount c t2 minus t1. So if this was g of z plus ct1, then at some later time, g of z plus ct2 would have moved to the left. And again, it moves with velocity c. We just need to clarify one thing about signs and propagation directions. It's not the absolute sign of z or ct in these expressions that matters. It's only the relative sign of z and ct. For example, f of ct minus z is still a wave going to the right, though its shape will be the opposite of the function f of z minus ct. So if this was f of z minus ct, then this would be f of ct minus z. Now, very often we are interested in what we call monochromatic waves. That is, the situation where the waves are oscillating at one specific angular frequency, omega. So we're saying the temporal behavior of the wave is of the form some function capital T of small t, which could be e to the I omega t, it could be e to the minus I omega t, it could be cos omega t, it could be sin omega t, or indeed any combination of these. Now, as a result of saying, well, the time behavior is always the same, it's the same at every point on the function in space, So therefore, we can split this overall wave function, phi of z and t, into a product of some function of space, which we'll call capital Z of z, little z, and some function of time, capital T of little t. As a result of that, when we take the second time derivative of phi, we always get minus omega squared times phi. That works, taking the time derivative of any of these functions, or indeed any combination of them. So that when we look at the wave equation, because we can substitute for d2 phi by dt squared being minus omega squared phi, our wave equation for the spatial part that is left turns into this form, where k squared is omega squared over c squared. So we just simply substitute this expression for the time derivative into our wave equation, and we're left with this part here for what's going on with the spatial part. And this is called Helmholtz's equation, which we encountered before. Now, a very important point about wave equations is that the ones that we're interested in, at least, are linear. That is, for this wave equation here, and therefore also the Helmholtz equation, because it's just a special case of this one, they are both linear equations. That is, if phi 1 of z and t is a solution of the equation and phi 2 of z and t is a solution, then so also is any combination of them, where these are arbitrary constants a and b here. And that is what we call linear superposition. And many of the waves that we want to work with show linear superposition. A particular example of linear superposition is what we can call standing waves. So if we take an equal combination of forward and backward waves, so here's a forward wave here, and here's a backward wave. I've just taken an equal linear combination of these two sine forms. We can also, by the rules of trigonometry, rewrite that in this form. These two are exactly equivalent to one another. And here, again, k is omega divided by c, the wave velocity. This gives us what we call standing waves. So we're going to look at our rope tied to two walls at either end, and we're going to choose a specific value of k equal to 2 pi over L, and omega therefore equal to 2 pi c over L. And these choices satisfy the boundary conditions that the wave has to be zero on these two walls. There are many other choices we can make here that also satisfy these boundary conditions, and you can guess what they are. I've chosen a specific example here where our rope goes both up and down. We could have had one where it just went like this, or one where it goes up and down again, and so on. We'll just look at this one here. So with these specific choices of k and omega, we get a wave that satisfies the wave equation and satisfies these boundary conditions, and incidentally is a summation of an equal amount of a forward wave and a backward wave. It's really the sum of a wave going like this and a wave going like that at the same time. So let's look at what happens to this wave here. That's the classic behavior we see for standing waves on a rope, and it's an excellent example of both linear superposition and the overall behavior of wave equations.